who will be talking about high angular momentum halo gas.
All right, thank you. And thank you to the organizers. Such a great workshop so far. I'm looking forward to the rest of the day as well. So this is work that we posted on the archive a few months ago, beginning of the summer, about the angular momentum of not so much galaxies, but galaxy halos is what we're going to be talking about. And hopefully I will try to convince you that there is at least something that is robust across different simulations types and code types that we can all at least agree on, even if it's just in a qualitative sense. So before we start talking about angular momentum in galaxy halos, let's just kind of remind ourselves of kind of the picture of angular momentum growth in galaxies. So here we have our silly little cartoon example of kind of a proto-galaxy that's accreting gas. There's gas in the halo, flows in. The kind of angular momentum of the incoming dark matter and gas are both set earlier times by large-scale tidal torques. The gas kind of shock heats to the virial temperature of the halo and mixes. And we would expect the kind of distribution of angular momentum, spin parameters of the gas and the dark matter to follow each other. You know, from n-body simulations, that should peak around lambda of 0.04-ish for n-body simulation halos with some broad distribution of different spins depending on exactly how it assembled there. And then the gas cools out of the halo, condenses onto the galaxy, and so right kind of the toy model approach here, we have kind of the size of your disk should kind of roughly be the spin parameter of the dark matter halo and kind of the size of the halo. Right? And this turns out to work pretty well for kind of getting distributions of disk sizes and things like that for galaxies. The question is does this picture work very well for that kind of intermediate step of what the angular momentum of the halo gas looks like? Right, so there are a couple kind of maybe issues we'd have with this picture if we're trying to think about what the CGM around the halo is doing. One is we know kind of from more recent theoretical models and simulations, right, the gas doesn't always necessarily shock heat, right? You have this cold flow picture. In very massive galaxies, even at high redshift, right, the streams, in my silly cartoon again, right, the streams can kind of penetrate the hot halo and make it down to the galaxy, or at least near the galaxy. There's argument now about whether the cold streams make it all the way to the galaxy or not. But at the very least, they penetrate for a decent while into the halo. Now, that's actually not what I'm talking about. I focus more on kind of Milky Way size things, right? So kind of a Milky Way progenitor at high redshift is not such a high density peak that it has 3 or 4 very, very massive kind of filaments flowing all onto the kind of the node of the Milky Way. That would be much more massive. The Milky Way at kind of Z of 2 or 3 typically tends to sit more in the mass regime of kind of sitting in a filament. So it's not quite isotropic because there's still preferential accretion kind of from the couple directions. Maybe there's a weak little third stream coming in, but it's not quite this same picture as, for example, Avishai's talk is talking about just different mass regime, just to keep that in mind. But still not completely isotropic, right? It's coming from preferred directions along the cosmic web. You still have this kind of cold mode picture. It looks a little different. From the kind of observational stance, if we have this picture that the gas in the halo has about the same spin as the dark matter, and if it kind of cools and conserves angular momentum, it has kind of about the right of angular momentum to kind of make a rotationally supported disk galaxy about the right sizes. Then one issue we have with that picture coming from observations is, what about things that look like they have more angular momentum than that? Right? So either you have kind of more extended structures. Here's a kind of, in the local universe, kind of extended H1, right, disk, much bigger than your typical kind of galactic disk. Here's the Milky Way for comparison, right? Where's that angular momentum kind of coming from? If all the gas in the halo is supposed to be spinning around with just enough angular momentum to cool and make a disk, what's going on here? Or kind of more kind of intermediate redshift, right? We have absorption systems, right? Here's a kind of galaxy. You get enough information to get the rotation curve of the galaxy. You have a quasar line of sight up here that you can get an absorption systems from. Here's some lots of great work on this. Here's an example from Boucher et al. 2013. And then these absorption systems, there seems to be this bimodal distribution. If you're along the minor axis of the galaxy, it kind of looks like stuff flowing out. But absorbers that tend to be kind of along the major axis of the galaxy, even when it's 30 kiloparsecs away, seem to often kind of co-rotate with the galactic disk. Here about like 200 kilometers per second or something. So relatively fast, kind of co-rotating stuff, like how does that fit into this picture of angular momentum? Or we heard some great talks this week even. So yesterday, right, Chris Martin talking about his observations of these kind of giant proto-galactic disks, right? You get the kind of kinematics. You see, maybe he cautioned, like, okay, maybe we could argue over whether these things are disks, but at the very least they're kind of rotating. They have angular momentum. It seems to be kind of connected to the kinematics of the filament, right? And if you calculate the spin parameter for these big disks, it's like lambda 0.1, 0.2. We even had one that was like 0.3, right? Which is crazy if you're comparing to the dark matter, right? 0.04 to 0.3. What in the world is going on here? X even gave a talk, right, earlier as well, where he kind of posed the question, like, what's going on here with this enormous Lyman alpha blob, right? Whether you want to say this is a disk, maybe not, but at the very least, we have this kind of bulk sense of halo gas swirling around with this kind of coherent rotation. How does any of this make sense in that picture of kind of hot halo gas with the spin parameter of just the halo of the dark matter that then cools? Now, luckily, in the past few years, a number of kind of groups have looked at this problem. How does the kind of cold flow picture maybe change our picture of how angular momentum works in galaxy halos in particular? Now, one thing to keep in mind, and this isn't necessarily new, right, but later accreting stuff has higher specific angular momentum, so there is a distinction you want to make necessarily. If you're looking at all the dark matter in the halo, you're asking about kind of add up all the angular momentum, everything that ever came in throughout the halo's entire history. The thing about looking at gas in halos is you're not necessarily looking at a total cumulative average history of everything that ever came in, right? Cold gas is going to sink quickly down to the galaxy, so if it's still out in the halo, it probably came in recently, and recent accretion tends to have more specific angular momentum. That's just kind of an aside, but in addition to that, right, so this is an example from my 2011 paper or something. We looked at a hydrodynamic cosmological zoom in of a Milky Way and just kind of calculated the spin parameter of kind of the dark matter. Here's your 0.04-ish, right? But then also the gas, the hot gas, the cold gas. We can see significantly more kind of angular momentum of the cold gas in the halo. This isn't a result only we had. A number of groups are kind of finding this, right, with different codes, some of them big statistical samples of thousands of kind of intermediate or lower resolution simulations, right? Some of them are, run zoom-ins. What we're kind of finding is, yes, as we know, the cold mode gas accretion on this scale is, not isotropic. It's flowing along the filaments. These filaments respond differently to kind of tidal torques, right? They end up having higher specific angular momentum. So Danovich et al. Did a good analysis of that, looking at the kind of inertial tensor of the filaments versus what you might expect. That sinks quickly if you kind of track the cool gas, right? That's kind of the whole point or part of the point of kind of cold flow paradigm is it doesn't kind of shock heat and stay in the halo for a while. Sinks in a couple free fall times, kind of spirals in. One of the results we had a few years back was that sometimes, not always, right, it's spiraling in with this high angular momentum. It's relatively coherent because it's all recent accretion. It hasn't been time for kind of misalignment of the filaments to do any vector cancellation yet. And you can get these really extended things, right, that kind of look like us to a disk, so we call it a cold flow disk, right? But it's not rotationally supported. It's not kind of solid here. It's kind of clumpy and patchy, and it's spiraling in 1 to 2 orbits. Now this kind of fits what these observations have been looking at, right? You would expect kind of co-rotation of gas out here versus the inside. You might expect to see this kind of velocity shear signature if you could take a big picture of this halo in observations. And of course, what happens with the actual galaxy is much more complicated. Then you're looking at kind of the cumulative distribution of all the cold gas that ever sunk onto the galaxy. You have vector cancellation, misalignment, feedback blowing stuff out, right? So we're not trying to say that this picture makes galaxies that are much, much bigger than you actually see, because that's not reasonable. But the halo is doing something else. But our question was, how robust is this, right? We ran this in kind of a gasoline simulation with a particular set of feedback, a couple different types of simulations up here with different sets of feedback. Is this picture something that we can start claiming is like qualitatively robust, or is this just some weird thing you get in one simulation and someone else runs a simulation and they don't see anything like this, right? So that was kind of the question that we were hoping to probe at. And so what we did is we run a comparison project here. We ran Milky Way mass halo, 5 identical initial conditions, but we ran them with different codes. And so not at the level of what kind of Agora is doing, right, but kind of a simpler version of that. Instead of trying to make sure all the physics is exactly the same, we're not trying to look for how the codes are different. We know they're going to be different. We're trying to see if they qualitatively agree on anything, right? Even if you let all the simulators use their favorite, right, full physics implementations that they always like to use in kind of recent works, and so that's what we did, right? So Repo, Enzo, Ramses, Art, Gizmo with the PSPH, with the fire feedback, run your favorite feedback, right? And then we'll see if they agree on anything. Our particle, some of our kind of statistics down here of resolution, about 95 parsecs mass resolution. And we did an identical analysis routines thanks to YT. So YT is awesome for doing the exact same analysis, right, on different simulations. We're going to focus on kind of high redshift here, 3 to 1. So here's a quick kind of picture of what we have. We have our kind of Milky Way progenitor thing sitting in roughly kind of a filament. This is at redshift 3. You can see the kind of basic large-scale structure is similar, but right, the details vary exactly how many streams are coming in, exactly where the kind of little satellites are coming in, the exact structure of the galaxy, all those things, not surprisingly, different codes with different feedback physics, different star formation prescriptions. Obviously, all the details are in the paper. Right? They look very different. The temperature especially, right? What exactly is happening to the CGM based on your kind of star formation prescription? How hot does it get? How kind of thin are the streams? All of these things kind of vary substantially between the simulations. Again, not surprising, right? The physics is different and there are different codes, right? But what about this picture? Is it still true that the halo gas has this higher angular momentum than the dark matter? So let's look at that. So again, spin parameter as a function of kind of time here, right, from redshift 3 or 4 down to 1 or so. The different symbols are different simulations. Depending on who ran what, we have the simulations at slightly different kind of snapshot outputs. We kind of plot them all on one thing, and what we see, kind of general trend, they all basically agree, right? Dark matter spin parameter is still about 0.04. Those dashed lines are kind of just the average in this range of time across all the different simulations. But again, now maybe at very, very early times, right, if the streams maybe have more comparable angular momentum to the dark matter. If you go beyond redshift 4, 5, 6, I think there's some results on that even of like the low angular momentum of very focused streams at redshift 6 or 7 or something. But in this range, one thing they do seem to all agree on, right, if you just look at the cold halo gas around the galaxy, now here, incidentally, we've cut out the galaxy itself. This is everything outside of 0.1 times the virial radius. We were interested in the halo gas, not the galactic, right, stuff. And so significantly higher with an average, right, significant spread here, right, depending on different simulations. So quantitatively different, but about 4 times the spin of the dark matter. Now, it would have been way too confusing to plot the kind of hot gas on here, too. It showed an average about 2 times the spin of the dark matter, so not nearly as significant as an effect as the cold gas. But here, at least, we see some universal similarities. All right, so if you have high angular momentum cold gas in the halo, kind of flowing in from the streams, do we still get this kind of bulk rotational signature or not, was kind of our next question. So now we kind of zoomed out here a little bit. I just want to get a little more sense of kind of the environment of what's going on around this particular galaxy. Here's our 5 codes again. You can see the basic kind of large-scale structure. The thing I want to kind of focus on down here, I have kind of the line of sight velocity of this stuff down to, of course, densities we could like never observe at very low densities, so we can see all the streams. All right, and mostly what I want you to point out is that if you pick kind of an arbitrary orientation and just kind of view your galaxy in some arbitrary direction, and you're a kind of a Milky Way sitting in a filament, right? Odds are you're not going to pick kind of the perfect orientation so the filaments are perfectly perpendicular to your line of sight, right? And so as you kind of would naively expect, right, what you're going to get is some signature of kind of the flow onto the galaxy at the scale of the virial radius, right? So kind of just to kind of help your eye, right, this upper stream up here, all the simulations can agree on basically it's flowing in, and because of this projection, right, the kind of line of sight velocity is kind of blue shifted to that entire stream flowing onto the galaxy. Whereas these two down here, because of this same projection effect, right, it's kind of redshifted and all these different simulations flowing onto the galaxy. Now, if you kind of track this same basic trend and now zoom into the virial radius, we see basically the same thing, right? Here's that filament we just looked at in all these codes. Here's the two bottom filaments we were kind of looking at on the kind of large scale environment. And so it's flowing in, and you see this, you see this same effect. Go back. Okay. You see this same basic signature, right? You have these streams, they have high angular momentum. Another way of putting it is they've gained some kind of transverse motion, and so there's kind of an impact parameter as they come in. You can imagine kind of shooting two fire hoses of stuff with an impact parameter. It's going to swirl around as it sinks into the potential well, right? And so you see this kind of blue shifted on top, red shifted on bottom. Gizmo's really weird. We're going to talk about that in just a second, so ignore that one for now. Other than that one, right, you see this basic trend. Now, in a previous kind of paper a few years back with the gasoline code, we saw something like this, and it was like a nice, thinly defined kind of disc-like looking structure, right? Here, the kind of exact kind of morphology of these things is very different, so I'm not sure what we should call it, right? And previously, we called them kind of cold flow discs. Some of these kind of look disc-ish-like. Some of them don't, right? So I don't know what to call this, the cold flow messy stream region or chaotic in-spiraling stuff, right? So we can argue over what words to use. Maybe we should take a vote later. But this kind of bulk, high angular momentum, coherent rotation seems to be, in a qualitative sense, right, predicted by all of these. Now let's talk about Gizmo for a second, because I just said predicted by all of these, and this looks kind of crazy in comparison. What's happening is, right, the exact timing of, say, mergers that are going on is slightly different among codes. We wanted to compare them all at the exact same redshift, but Gizmo is like in the middle of a post-merger kind of explosive feedback starburst thing going on right here. If you look a little closer at that, and the movie's supposed to play. Go, movie, go. Maybe if I click on it. It was working earlier. Okay, well, that's a disappointment. Okay, well, I guess we'll have to forget the movie. Sorry. I can show you later if anyone's interested in watching the movie. Here's the snapshots right around that epoch. Here's what we just saw in that past kind of picture. What you can notice is immediately before this crazy outburst event, right, you had this same signature, the kind of bulk rotation because of the inflowing filaments. And in fact, immediately after this thing is over, the streams are coming in, right, with such mass influx, such high angular momentum, it kind of immediately rebuilds this signature right after the crazy outburst is over. So yes, it doesn't look exactly like it right here, but that's just because of weird timing of the fire feedback being in the middle of kind of destroying the whole CGM of the galaxy. But it resets itself very quickly. All right, now what about less than Z of 3? So here we took some kind of representative examples of our simulations at various different time steps, various different redshifts here. We have this kind of flowing in ART. We have Ramses and Repo. All of these are at Z of 2 along the same projection. All these are at Z of 1.5 along the same projection. You see, obviously, the extent of these things kind of dies down, right, as the cold streams get kind of not so focused anymore, right, at lower redshift. But even then, you still see this basic trend that the gas has high angular momentum, even if it's not so high a covering fraction and certainly stops looking like a giant disk in any sense of the word. But this bulk rotation, this high angular momentum, this basic trend to tend to co-rotate with the galaxy as it's streaming in, seems to be relatively universal. All right, so just kind of to sum up, so our motivation was trying to see if we can modify our kind of basic picture of angular momentum acquisition so that we can understand what the angular momentum expectation for gas in the halos of galaxies should be. Our kind of approach, based on some previous results that had kind of already done large statistical samples for a single code, we just kind of zoomed in on a high-resolution example of the Milky Way and used a bunch of different codes to see if this widely varies or if this is expected to be relatively robust, if all the codes agree to some degree. It seems that they do agree to some level, right? The cold halo gas is higher angular momentum, higher spin, roughly 4 times the spin of the dark matter, but considerable spread. The kind of basic structure and kinematics of the cosmic web, not surprisingly, are in agreement between the codes. You get this steady inflow of high angular momentum gas coming in, right? The kind of short sinking times help this to be coherent because there's not really time for kind of the alteration and misalignments of incoming stuff to kind of vector cancel out. And so you get this coherent rotation that should be linked kinematically to the inflowing streams. And so this results in whatever you want to call it. I think we call them cold flow disks, but obviously a lot of people don't like using disks for non-rotationally supported, chaotic, clumpy, messy things. So we should probably rephrase that to something else, right? Chaotic in spirals. I don't know what else to call it, right? But something here is going on. Just bulk rotation. If you have a favorite terminology you think we should start using, come talk to me afterwards, and we can get some feedback from you guys. And of course, the details vary considerably among the codes, but that kind of basic picture is the same among them all. Thank you.
So I'm going to take the prerogative and ask a really quick question. This number 4 here, how much halo-to-halo scatter is there on that? And is there any sense of how much it varies with some physics? Like, if you have different reionization history, for instance, does that affect this kind of thing?
So we have, because we were still trying to figure out if this is even robust across simulations, we haven't really looked at the exact details, even amongst, obviously, like the exact same initial conditions, kind of just evolving from Z of 3 to 1, we saw a huge scatter. So I would imagine, that's why they're twiddly there, I would imagine there's considerable variation there, but the things that seem to be robust is just that it's significantly higher than the dark matter.
Okay, I think Avishai got in there just first.
Just to repeat what Kyle said, this factor of 4 is made of 2 factors of 2. One of them, well, Kyle, either 2 squared or 2 times 2, or 2 plus 2. So 1, 2 is because the gas is new, and the dark matter is an integral of the past. Even the dark matter, when it enters the halo, has a factor of 2 more spin than the old dark matter. This is one factor of 2. The other factor of 2, as Kyle said, is because tidal torques affect the very narrow gas streams much more than it affects the very thick dark matter filaments, because the quadrupole moment is much higher. This is 4.
Hi. So I just want to verify since these are all the Milky Way progenitors, you don't have you don't have a hot halo that the streams are going through, correct? In most of these simulations.
Compared to a much more massive system, right?
Sure.
Like, no, yeah.
Okay, and I'm just curious, could you estimate approximately what the typical resolution is within the filaments, kind of at the outskirts of the virial radius, compared to the size of the filaments?
That number I don't have a good feel for off the top of my head. No, we haven't really looked at the scale or size of the filaments coming in.
All right, thanks.
One more question, just while we switch over.
Earlier, the difficulty for a lot of models is because cooling happens in the very center of the galaxy of the halo. Mm-hmm. So the material really give you the disk has very low angular momentum. So then people like Aaron Dutton and myself had to think about how to get rid of low angular momentum material and make the disk relatively more extended. Right. So your specific angular momentum for the material has much higher specific angular momentum than the halo. Yes. So do you think so we have to be thinking about how to get rid of higher angular momentum material?
Well,
or dynamical friction or some existing physics can
so we haven't looked exactly at how the exact process for the gas losing its angular momentum so you don't make a disk 3 times larger than what we thought, right? But my intuition would be, right, if you look at the kind of cumulative history of all the stuff that's come in dark matter, that's where you get this lambda 0.04. The thing I would want to stress about the halo gas is part of it, as I was saying, is because it is recent accretion, right? There hasn't been kind of vector cancellation over long time scales, misalignment of the incoming angular momentum vector. My kind of 0th order guess would be, right, there shouldn't be too much of a problem because as you add up all the gas over a cosmological time scale, you're going to get this misalignment, and so there will be cancellation of angular momentum just like you have with the dark matter.
Okay, thanks very much. Let's thank Kyle one more time.
Thank you.